Hi everybody, my name is Manish. I'm an applications engineer here at Prensia, and today I'm going to be discussing how you can create an equivalent damage durability test using nCode GlyphWorks. Before we go into the presentation, here's just a quick look at the agenda. Firstly, I'm just going to give you a bit of background on who we are and the software that we sell. And then we're going to take a deeper dive into how you would go about creating an equivalent damage lab test. This will be followed up by a fairly lengthy software demonstration where we will go through an entire process, building up an equivalent damage analysis process. And then finally, we will go to some questions. So a little bit about Prensia. So Prensia is a software brand that sits within the HBK family of companies. Prensia is made up of two individual software companies which were merged, that is nCode and Reliasoft. I'll give you a bit more detail on the software that we sell on the next slide. But other things that we do, we're quite heavy in training and education, so we do offer quite a wide range of training courses, both online and post-pandemic. I'm guessing we'll be going back to doing those face-to-face. And as well as that, we do offer some things in terms of services. So if you have materials that need characterizing, we can do the characterizations of that. And we also have some consultancy services where we can help you perform some asset management tasks and also help aid in the design and development of your products. This is the overall Prensia software portfolio. Starting in the column on the left-hand side, we have a set of tools that are tailored for reliability analysis. So that is working with failure data, test planning, and system modeling. The column next to that contains tools for the management of reliability. So things like FMEA analysis, reliability-centered maintenance, and also X-Fracassa, how you then take in your failure data from your customers and then action those. On the right-hand half of the screen, we have the nCode family of products, starting with Design Life, that is CAE-based fatigue analysis. Beneath that, we have GlyphWorks, which is signal processing and also strain gauge-based fatigue analysis. And finally, VibeSys, which are our tools for frequency-based analysis and also some sound analysis too. And finally, on the very right-hand side, we have two web-based tools, Akira, which allows you to democratize your analysis, and automation, which is for data storage and reporting. The main tool I'm going to talk about today is nCode GlyphWorks, and that is what will be followed on with the software demonstration towards the end of the presentation. So moving on, let's have a little look at the background on why we do equivalent damage tests and why they're important. So as engineers and designers, it's pretty well understood that we have to validate our products before we send them out into the field. Just taking a look at that image down at the bottom, if you are creating if we have this hook component that is holding this pilot off the ground, we need to be sure that this product will do its job accordingly, because if it doesn't, obviously it could be quite detrimental to the life of the person who's on the other end of it. If you can imagine that we have a load transducer on the end of this hook, we can calculate some loads from the field, and you can see that it's quite highly variable. The difficulty becomes, how do we then take this variable load and reproduce something within a lab environment which is controlled and repeatable? The other key thing that we need to work out is this lab test actually representative of what is happening out here in the field? Within the nCode GlyphWorks software, we have a few different methods of being able to replicate real-world loading. So starting from the top, we have a constant amplitude test and a block cycle test. Moving on, we have something that acts more in the time domain. So if you did want to rerun a full real-world signal, we have some tools which will allow you to sort of gate out some of the smaller damaging cycles so that you have a test signal which contains only the damage content that you are interested in. And then finally, down at the bottom, if you are working in an NVH type type area, then we have some tools which will allow you to create a PSD which you can use to drive a shaker table in order to test your components. The two that we are going to focus on today is the constant amplitude test, and then I will follow that up by showing you how to create a block cycle test, which is representative of the loading, real world loading that your products will experience. So why would you use a constant amplitude test? So if you can imagine going back to that hook that was there, if we are the manufacturer of that hook, it is really not practical for us to have to take that out into the field and perform maneuvers like you see on the left-hand side regularly in order to just test out those components. If you are just the manufacturer of that hook, you probably won't have access to a helicopter very easily. So you can see if that was the route that you were to take, it would become very expensive very quickly. So a cyclic constant amplitude test is what we would use back in a lab environment. As you can see, it's probably much cheaper to buy one of these bits of equipment than it is to get a helicopter out in the field each time you need it. It's relatively cheap. It's a simple test, and it's used in almost all industries where components are designed for use out in the real world. And the idea behind this is that we have this highly variable loading signal down here, which is representative of what the real world is. And we need to create a signal which contains the same amount of damage in this test environment as there is in this real world environment. As well as that, if you were to do this using finite element analysis, if you were to run a full complex signal, which could, for example, contain 100,000 turning points in it against this FEA, it would be quite expensive in terms of computation. So it could take a very long time in order to basically run that analysis. So again, this could also be used to create a simplified loading signal that can be used to run your finite element analysis. So onto the software demonstration. Just before we go into it, I'll just give you a quick overview of the sort of steps that I'm going to go through. Firstly, we have a real world signal that we have that we want to replicate. We're firstly going to assess the damage of that, and then we're going to create a simplified sine wave type loading signal, compare the damage to the real world signal, and hopefully come out with a value on the other end, which tells us how many times we need to repeat that in order to create an equivalent damage. And then we will extend that further by creating a block cycle, just so that you have a mixture of different loads within your test. So if you just bear with me, I will switch over. So for those of you that have never seen the software before, this is the nCode GlyphWorks software package. On the left-hand side, we have the available data window. I've already pointed it to a folder of data, so I can just expand this and take a look at the files that I have. I have this single test file here, which contains one channel of data, which is in force newtons, and I can just drag that straight into the middle of my workspace, display it, and I can expand that. So as you can see, this is our real world loading signal that we have. You can see it's highly variable, so it would not make sense to run this fully. So what we need to do is basically replicate the damage from that. On the right hand side, we have the Glyph Palette. So in here we have a series of functions which are all organized based on what they do, and they are basically drag and drop. So if I just start by building the overall process, so I can go down to the palette, I can drag in that block there. And then as you can see, the blocks have pads which are color coded, and then I can connect them to each other in order to build the overall process. So let me just go ahead and continue to make it, and then we'll talk about what each of the pieces do once I have it all up and running. So I've now pulled in a metadata display. to take a rainflow cycle count of the signal too, and also connect a display to that. Okay, so this is the first part of the process. I'm aiming to assess the amount of damage that is contained within this signal. And in order to do that, we are going to perform what we call a relative damage calculation. So if I just open the properties, so each one of these functions has its own set of properties. If I open that one, we can see what we are doing in here. So the potential damage glyph is used to perform a relative damage calculation. If you were to perform a full fatigue analysis, you would generally need a SN curve if it's a stress life analysis. But in this situation, because it's only a relative damage calculation, all we really need to do is supply it with the slope. The default value in here is applicable to is already applicable to the material I'm going to use. So all I have to do is enter the intercept. The intercept in this case is arbitrary. It doesn't really make a difference what I enter in at this stage, because what I'm aiming to do is perform the same calculation with two different signals, and provided that I've used the same material properties, it should give a comparable result for the two. So if I just press OK on that, hit run. So the data has flown from the left-hand side through the analysis process here. We have the potential damage glyph performing the sort of bulk of the analysis, and it will output that result in terms of metadata. As well as that, I'm performing a rainflow analysis. So what I'm trying to do is quantify the type of loading signals that we have in that input, in the input signal. So we can take a look in here and see that we have performed a potential damage analysis, and we have a value for damage against that. As well as that, we can take a look into here, look at the top view, and we can basically see what the damaging content is in here. So these are all the cycles. We have the range, so the overall max and min of the cycles, and the mean, whether it's compressive or tensile, so on. As you can see, we have a fairly thick line of blue, so there is quite a lot of signal content in here, which is fairly consistent. And then the further out we get to the right, it sort of scatters a little bit. So that is the damage content of my input signal. What I now need to do is basically create a simple sine wave so that we can then compare the damage from the two and see if we can produce a test from that. So in order to create the simplified load, I need to come back to the input palette and drag in what we call a time series generator. Now I will connect a display up to that so we can see what we're doing in there. And again, I can open the properties of this glyph here. So the operation is to produce a sine wave. I'm going to leave it at a total time of 1 second. What I need to do is just state an amplitude. So again, if we just come back to here, we have this little yellow box that may be a little bit difficult to see in the top left corner, but this is telling us what the range is and the mean is of where I'm hovering my mouse currently. So we can see after around 1700, after around 1700, the data sort of scatters, so the cycle I'm going to pick will stick it at 1700, so hopefully it sits within the input data. So back over at the time series generator, I can state the amplitude of my sine wave. So remember, 1700 is the overall range, so the amplitude of my sine wave needs to be half of that. So we'll say 850, hit OK. We can just take a look. So this is the sine wave that I've created. So this is potentially the amplitude of the cyclic test that we are going to perform. Now all that's left to do is to calculate the amount of damage in here and compare that to the damage that we have here. I think I need to do that. So I need to merge the two data streams together. I will bring in a test combination. I can pick that one there, and I can pick this one here. Just move this out of the way. And now I can replace these pipes with this one because I've now created a new data stream. So if I right-click disconnect, right-click disconnect, I can connect that there, connect that in place there. And now we can hit go, and you can see that we now have 2 channels worth of results. Within this display, it normally sort of populates it as a tree, but we can also convert this into a table, just so it makes it easier to see what we are looking for. So the first thing I want to do is jump into the table screen, select the area of metadata that I'm interested in. So I just want to add all of that to a table, and I would also like to add a channel title to the table as well. We can move that up. As you can see, rather than looking at it in terms of a tree, it's much easier to see the results that we're looking for. So this is the amount of damage that that single sine wave produces, and that is the damage from our real world loading signal. The last thing that's left to do is to just calculate the ratio of these two here. Now, within our software, we can calculate single value results as well, and we do that using a tool called the Metadata Calculator, which I can drag and drop it in place here, and I will need it to sit in between that display and that potential damage glyph. I can open the properties, run the data up to here. We're going to call this, give the result a set name and an item name. So this is the number of cycles. Set the data type. I'm going to call it a float, and I just need to divide the result from channel 1 divided by the result from channel 2. So check that box, come into here, find the damage, I click it, and you can see it's already populated that in there for me. I can use the buttons here to add in the divide symbol. I can divide it by that there. Add that to the list. And this time when I hit run, it currently hasn't populated because what I need to do is go back in here and just add that bit of metadata to the table I've created. So we add that there. And now we can see that the number of cycles is 204 of the input of that sine wave. So if I repeat that sine wave 204 times, it will produce the same amount of damage as that input load. We can also check to see if the cycle that we chose is representative. So in here, if I change this display to 2 and resize the histograms so that they both have the sort of same maxes and mins, this is the sine wave signal here. I know it may be a little bit difficult to see, so we have this blue dot. And if you see, it tracks a cursor over the top display at the same time, so you can see it's actually in the range of the real data. So this sine wave that we've chosen is actually representative of our real data. It hopefully shouldn't produce any different failure modes than is currently there. It's quite simply how you can produce a constant amplitude test. Now, the next step is it a wise thing to only pick a single sort of load range for your test? And it probably isn't. So what we may want to do in this case is pick a mixture and make this test lab signal a bit longer than it currently is. So again, what I can do is right click, hit this duplicate button, and it will copy that. I can now open the properties, but before we'll do that, let's pick some extra cycles to use. So this is a 1700 one. We can pick one at about the 1000 range, I think. As you can see, there's quite a thick blue band there, so that's something reasonable in there as well. And if I go back down here, we could probably pick something at the 500 range as well, and that will also produce some cycles that are representative of our input data. So starting with the 1000 range cycle, I can come back in here and just change the properties for this. So again, range of 1,000, half it to get the amplitude. I can say 500. And what I now want to do is to join those two signals end to end. So I drag in the concatenation glyph, connect those two in place. And in here, I can now set a repeat count. So the further to the left on this histogram, it would normally indicate there are more cycles of that within the data. So I can now set a repeat count for that pipe too. So I'm going to say that that's that 1000 amplitude signal. I'd like to repeat that 3 times. We can just take a quick look at what effect that has in the display. So we can see we have the first cycle once and then the second cycle 3 times afterwards as well. And we'll add another one here too. So I can right click and duplicate again. And I can do the same with this concatenation glyph because I'm going to need that again. But this time I want to have a cycle which has a range of 500. So if I put 250 in here, now connect that to there, this to here. For this second one, I would like to set a repeat count of, let's say, 5. Now, when I hit run, we can see that this is our new signal that we are potentially going to use to run a validation test against. So we have our initial cycle, which is 1700 range. We have our next one, which is 1000 range. And then we have our smallest one, which is a range of 500. We can go back to this histogram display. What to do? And now I just need to connect this back into series because this is now a new loading signal that we're going to do the comparison of. So if I disconnect that there, add that there, and here. We can now take a look and see where that falls in within our data. So if I just resize the histograms again so they're both sized the same, this is our 1700 loading cycle. This is our 1000 range loading cycle. This is our 500 range loading cycle. So you can see they sit well within the data itself. And now, because the rest of the process is still set up from the first time that we did this, this table will contain the results that we're looking for. So we can see that the damage has gone up, obviously, because we have more cycles within the input signal. But when we maximize that, we can now see that if we run this test signal 117 times, it will replicate the damage from the input loading signal. So if I just jump back to the slides. So again, the analysis was mainly centered around this potential relative damage glyph that we have. It's key to remember that what we are actually calculating is this figure of relative damage. It's not absolute damage because it doesn't use a complete SN curve. It doesn't require any knowledge of component geometry, again, because there's no strain gauges. This isn't strain data that was using to load into it. It was actually a force. This is a good method for taking any type of loading data and being able to basically calculate a value of relative damage just in order to quantify really how damaging that signal is, particularly if you're using it to perform a comparative damage analysis. If absolute damage is something that you are looking to obtain, then you would probably have to use something like finite element analysis or perform strain gauge based fatigue analysis. So to summarize, I've hopefully shown you how you can take some in-service loading and using a simplified SN curve, produce a simplified constant amplitude or block cycle test. And again, this can also be extended into the finite element world. So instead of running that messy 100,000 point signal, we could create a simplified loading signal and use that to run your finite element analysis. And the key thing is, because we've checked it to see if those cycles are present in our input data, we should hopefully get some reliable fatigue results at the other side. So just to summarize, we have gone over how you assess the damage content from your measured load. We have created a simplified sine wave representing the test lab load. We've assessed the damage of both the test lab load and then calculated how many times we would need to rerun that in order to produce an equivalent damage when compared to the real world signal. And then we've taken that one step further and applied a block cycle loading, so it contains a mixture of signals, a mixture of size loads in order to run the test.